Hi there everyone and welcome back to NTE. In today's video what we're going to do is we're going to prove one of the Euclidean geometry theorems that you're required to know for your exam. Right. So the theorem that we're going to prove today is the one that states that if a line is drawn from the center of a circle, right, and the line is drawn such that it's perpendicular, right, to a chord in the circle, then that specific line bisects the chord that it connects to. Right. So in your exam, what's going to happen is that they're going to give you a sketch, right, which is already fully labeled for you to work off, right? So the first step that you're going to see me do in this video is not really going to be required for you because you are already going to be given the sketch, right? So your proof, right, is going to have all the letters that are actually included in your specific given sketch, right? So now in this video, what we're going to do is I'm going to construct the whole proof, right, from memory and from scratch, right? So when we look at the theorem, we see that the keywords over here, right, so the given things, right, that have to be in place, right, are these things of a center, right? So we have to have a center. Okay, we have to have a center. That's one of the keywords in this theorem. Another thing is that we have to have a line, right, coming from the center, right? And then another thing is we need a chord in the specific circle, right? So these are the three key components of this theorem. So let's quickly just construct it, right? So we need a circle, obviously, right? So we'll take a circle. Okay, so here we go. Here's our circle, right? In the circle, we need a center, right? So we're going to sort of locate the center of the circle, should be around somewhere over here. Okay, and you could in fact call your circle anything, but you would go with whatever label they used in your diagram. We're going to call our center O like usual, right? So there we go. We have the first part of the theorem, right? We have our center, right? We also have a label for our center. The next thing that I want to construct is a chord, right? And a chord, remember, is just a line connecting any 2 points on the circumference of the circle, which means that I'm not restricted as to where I can put the chord, right? I can put it anywhere I like, right? So what if I construct a chord over here, like that, right? And I call this chord Pn, right? Then I have the second part of my theorem, right? What's the last part of the theorem, right? It said we needed a line, right, which had to be drawn from the center, and this line specifically has to be perpendicular to that given chord, right? So that's the last component that we need, right? We just need to draw a straight line from the center to the chord such that that line is perpendicular to the chord. Okay, so now we've set up the theorem, right? What we now need to prove is that this line actually bisects this chord, which means that we're going to have to work with this middle point as well, right? So it needs a label as well, okay? We can call it D, it's fine, okay? So the way that you would set this out in your exam is that the picture would be given to you, right? And what you would say is you would start off by saying, okay, I am given, right, certain pieces of information which are in place, right, in the diagram, right, and then I'm required to prove something. Okay, so RTP means required to prove, right, and then after that I am going to have a few constructions that I'm going to make. Okay, then lastly you will have your proof. Okay, so this is the basic layout of all the Euclidean geometry proofs that you're going to do, right? So let's fill in this first section of the given, right? So what are you given, right? You're given a circle, center O, right, with a chord PM, okay. Okay, we can end that. Maybe let's put a comma over here instead of a full stop, right? So we're given a circle center O with chord PM, right? D is a point on the chord PM, right? Such that OD is perpendicular to our given chord PM. Okay. So now what are you required to prove? You're required to prove this last section, right? You're required to prove that PM, no, sorry, that PM is divided equally into PD and DM, right? So that's what the word bisect means. It means that these two lengths, right, PD and DM, right, have to be the same length, which means that subsequently D is the midpoint of this chord PM, right? So that's what you're required to prove, and this statement over here is the statement that should be the last part of your proof. Okay, so your conclusion basically, right? Now we're going to go on to any constructions that we need to make, right, in order to draft our proof, right? So the constructions that we're going to have to make for this specific proof is going to be radii, right? Because this proof, if you think about it, it just relies on these two triangles basically being congruent to each other. Okay, so the fact that we drew a line from the center of the circle, right? We've already played with the symmetry of this circle, okay? Because if you look at this, right, if you had to just extend this line, right, beyond the circumference of the circle, right, you'll see that that line is actually a diameter, right? So already what we've done is we've created two semicircles, right? And these two semicircles are already, just by the nature of the circle, congruent to each other, right? And what do we mean by congruent? We mean that those two halves are exactly the same, right? So now because of that symmetry in the circle itself, right, the fact that this line, it doesn't matter where we choose to put the line, right, wherever we decided to position our chord, this line that we draw, right, because it has to go from the center, right, that line is actually on top, right, superpositioned over the diameter of the circle, right, and the diameter of the circle divides the circle into two equal parts, right, we call those semicircles. Those semicircles are already congruent to each other, so that already reminds you or gives you a little bit of a tip, right, that this proof is meant to rely on congruency, right. So we're going to take away this dotted line because this is not the construction that we're going to need. I just put that in just to help you to remember that this is how you're going to go about this proof, right? Because the proof just relies on congruency. So there's a dotted line gone, right? So now we're going to go for our constructions, right? So the only constructions that we really need to do is the constructions of radii, right? So constructions, right, is going to be draw, or actually let's use the word join, right? So join OP and OM. Okay, so after writing that down, you would go to your sketch and actually indicate it, right? So we are joining OP and OM, right? So now we know that this 90-degree angle over here, right, will show up on both sides. Okay? And we can then maybe just do a further labeling over here just to make the writing out of our proof much easier, and call this one side angle D1 and the other side angle D2. Okay, so in our construction, right, you can even put over here, right, that what happens as a result of joining these two points, right, OP and OM, right, is that you create such that triangle ODP and triangle ODM are right angles. Okay, this part over here is really optional. You wouldn't really be required to put that, but if you wanted to, you can, right? So now let's just look at what we've created. Okay, so we have now two different right angle triangles, right? We have this one over here to our right, which contains the angle D2. Okay, we'll shade it in blue. Then we also have the other right angle triangle to our left, right, which contains the angle D1, and we can shade that in red. Right, so now we are ready to write out our proof, right, especially because now we've reminded ourselves, right, what we actually need to write down, okay, or focus on in order to get to this result over here. Okay, so the way that we'll set it out is now we're going to say in, right, triangle ODP and triangle ODM. Okay, now we're going to do a proof of congruency, so we know that we need to list three different points. Okay, so basically we have to prove that these two triangles are congruent, right? So we first started off with the triangle ODP, right, which is the red triangle. That's the red triangle. And then we have the triangle ODM, right, that's the blue triangle. So we just have to remember that all the information that we're going to list, right, the first thing that we list has to be whatever that item is, whether it's a side or an angle, it has to be located in the red triangle, and that has to correspond to that same item, right, in the blue triangle, right? So what is the most obvious thing, right, that we can use between these two triangles to prove congruency? Well, the most obvious thing is this common side OD, right? So OD is equals to OD on the other side, and the reason for this is because it's a common, or you can write a shade side. Okay, so now we have a side. What else do we have? Right, we have that angle D1 and angle D2 are both equal to 90 degrees. And how did that come about? Well, it came about because the theorem required us to draw this specific line, right, perpendicular to the given chord, right? Now, if it's perpendicular to the chord, we know that that angle there, where they meet, is going to be 90 degrees. So that's the next thing that we can state, right? But because we have to state the information about the red triangle first, we're going to write down angle D1 is equals to angle D2, okay? And the reason over here, you can just simply write OD perpendicular to PM, or what you can write is both equal to 90 degrees. Okay, these two reasons are equivalent to each other and you can use either or. Okay, what's the last thing that we need to do? Right, because we have a 90 degrees in our reasons, we obviously have to see that this is going to be the condition of congruency of right angle, hypotenuse, and side. Right, so we have the right angle, we have a side. We now need to look at the hypotenuse of these two right angle triangles. Right, are these two hypotenuses actually equal to each other? Yes, they are, because the two hypotenuses, right, are actually the radii of the circle, and we know that in any given circle, all the radii are equals to each other. Okay, so that's the last thing we can say, right? In the red triangle, the radii OP is equal to the radius OM in the blue triangle, right? The reason here is radii. Now, because we have all of these things in place, right, we can now conclude that therefore triangle ODP, right, is congruent, and congruent is these three horizontal lines, right? If we use another textbook, you might see this symbol. There's a squiggly line with two lines like that, right? This also means congruent, right? But this is more in American textbooks. We usually just use these three horizontal lines, okay, to indicate congruency. Okay. So now, for the second part, right, the way that you list the second triangle, some teachers will be finicky about it, saying that you still have to hold on to the same way that we name the second triangle when we just prove similarity, right? But other teachers won't be so finicky, right? That's because with congruency, really, if you name the other triangle exactly the same as what you did here above, it doesn't really matter, because at the end of the day, if two things are congruent, everything about them is equal, right? But some teachers will insist that you still keep to the same way that we name similar triangles, right? So in other words, once two triangles are similar, that's because they are equiangular. So then you list the second triangle based on the equal angles, right? The corresponding equal angles. So let's do that for this one, right? So we're going to have triangle, right? Now O is going to be this angle over here, right? Which is basically going to be congruent to this angle. So you're just going to write O, okay? D is that angle D1, which is equals to angle D2. So you're going to write D, and then obviously then P is going to be congruent or equal to n, right? And just by chance over here, it just happened that I had already named it according to the equal angles, but it could have happened that maybe you named this triangle over here triangle DON, okay? Then it would change over here, right? If you then now stick to the naming convention of naming the second triangle according to the corresponding equal angles. Okay. Okay, so what do we need to add to this? To finish it off, we need to add a reason for our congruency. And the reason is because we have a right angle in both the triangles. So we write R, okay? The hypotenuse of both these triangles are equal, right? And there is a common side equal in both of the triangles. So that's the reason for why these two triangles are congruent. Okay. Now, because these two triangles are congruent, right, every single aspect of these two triangles is equal, right? So all the three angles in the two triangles are equal. All the three sides are equal. You already saw that the hypotenuses are equal, and you have this common side, right? So then therefore, PD must equal DM. And then you end this off with a reason, and your reason is going to be this statement over here that we noted, and you can write since triangle ODP is congruent to triangle ODM. So that's it for today's video, matriculants. I hope you learned something, and I will see you guys next time.